Right for me. Ooh. And I'm feeling.
Hear what I say. We are the business today. Fuck shit is finished today. RT and J.
What is going on, everybody? It's your boy Average Leader here with another video. Today we're tackling 2-Sum 2. This question is commonly asked by Oracle, Amazon, Microsoft, Intuit, and ByteDance. If you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, comment down below and I'll make sure to do it for you. And with that all out of the way, here we go. So let's get into the problem. Given an array of integers that's already sorted in ascending order, find two numbers such that they add up to a specific target number. The function 2-Sum should return indices of the two numbers such that they add up to the target, where index 1 must be less than index 2. And we're given some notes. Your returned answers are not zero-based. Interesting. And you may assume that each input would have exactly one solution and you may not use the same element twice. Ooh, okay, I see. So let's dive into this example really quickly. So we see that given the list of these numbers and the target 9, the output is 1, 2, because it looks like it's these two numbers here that sum up to 9, and since it's not zero-based indexing, we just add 1 to these. So this is the 0th index, which becomes 1, and this is the first index, which becomes 0. Okay, so let's take a deeper look into what this problem is asking, and let's draw out some of these examples. So I took this example straight off of Leetcode, and essentially just recapping the problem, we just need to find two indices that sum up to whatever sum is given to us. So now in this case, the sum is 9. So how could we go ahead and find two indices that could sum up to that? Well, off the bat, like we see that 2 and 7 are like right here, and they sum up to 9. So maybe we can just start by initializing two pointers at the first two indices and just add those up and see if that equals a sum. And in this case it does, but now let's just say that the sum was actually 22, which is made by the 7 and the 15. Right, now if that was the case, then how would we do this? Well, the first thing we should do here is kind of think of the brute force solution. So the brute force solution in this case is to iterate through all pairs of integers in this array until one pair adds up to the sum. And it was given to us in the problem that we may assume that each input would have exactly one solution. So there's guaranteed to be one pair here that adds up to 22. So how would we do this? Well, I'd still use two pointers and I'd initialize them to the 0th and the first index, or maybe if I called the first index I, I'd just set the second index j to I plus 1. And after that, I'd get our sum. I'd keep calculating the sum every time I move my pointer. So right now, with these two pointers here, the sum is 9. And I make a quick check. Is the sum that we just calculated equal to our actual sum? No. So if that's the case, I would just move one of the pointers over. So now I'm just going to move the j pointer, which is always going to be the pointer on my right. I'm going to move the j pointer to the right. Now I'm going to recalculate the sum. I'm not going to call this sum, I'll just call this temp. Now once I move the j pointer to the right, I have to recalculate my sum. So now the sum is 13, right? And now it's still not 22, so what am I going to do? I'm going to move the j pointer again to the right, and now I'm going to recalculate the sum. What is the sum here? The sum is 17, so I'm going to go ahead and write that as my temp variable. But now 17 is still not equal to the sum, and now j is at the end of our array. So when this happens, all I'm going to do is move my I pointer up 1 and reset j to the I plus 1 position. And now j would be here. So now once again, I need to recalculate my sum. The sum is 18. Is that sum equal to the sum that we're looking for? No. So I'm going to move the j once again forward, and now I recalculate the sum, and in this case it's 22. So since this temporary sum is equal to the sum that we were looking for, we'd stop our program right here and we just return that value. And yeah, this would be a brute force solution to the problem. So why is this like considered a brute force? Well, it would have to iterate through this entire thing so many times to get to the final answer. But at least we have a starting point, right? We can easily achieve this type of iteration through like a double while loop or a double for loop. And I'll code that out really quickly just to show you how easy it is. Okay, so right now, let us go ahead and code the brute force solution. So first things first, let's initialize our first pointer. Our first pointer is going to be in the 0th index. So that would be this. I'll call it I. And I'll say while I is less than numbers.length, that's when we are going to initialize the second pointer. And the second pointer is going to be j. And remember, j was always I plus 1. Wherever I was, it was always right next to it. So j is going to equal I plus 1 here. And now we're going to say while j is less than numbers.length. See, now these two for loops are the reason we can iterate through everything. Well, I guess not these two, because we actually have to do, here, let me just increment these. Now, this double while loop will actually give us that iteration where we're going through every single pair of integers. And if you can visualize this, see, if we started I at the 2 and j at the 7, by the time j gets to 15 and has to reset back to 11, it first looks for wherever I is, and wherever I is, it's going to be right next to it by this plus 1. But how does I get changed? Well, I gets changed at the very end of that inner while loop. So that's how this type of iteration is possible with this double while loop implementation. So now all we're going to check is to see if the sum, our temporary sum, equals the target. And what's our temporary sum? Well, that is when numbers at the index of I plus the numbers at the index of j equals the target. So whenever, let's say if I was here and j was here, if the numbers at this index and this index equals the target, then we know we found our indices, and we're going to return an array that will contain those indices. Return new int I, j. But remember, our returned answers are not 0-based, so we actually need to add 1 to these. Oops, 1 to these. All right, and we're told that each input will have exactly one solution, but we still need another return statement in here so this code compiles and runs properly. So I'm just going to return null outside, but this null should never get triggered. So I'm going to run this real quick, and let's submit it. All right, perfect. So you can see how slow this is. This is what happens when we're running a brute force solution. The runtime for this particular solution is O of n squared, because we're literally going through every single pair of integers, and we'll usually get like an n squared type runtime when we have like a double for loop or a double while loop. So that was the big giveaway here. And the space complexity is just O of 1, since we're not actually creating any new space, even though we have this int array at the end. Remember that the return storage doesn't actually contribute to our space complexity. So space complexity here is O of 1. So, L of n squared, that's like great and all, and that's a good starting position, but like we need to make that more efficient. An L of n squared solution would not fly in an interview setting if there was a better solution. So now we got to think, how can we make this a little bit better? Let's go back to the drawing board. All right, so how can we make this more efficient? We're given one, I think, very important piece of information, and that is that this input array is sorted. Now, we still could have used our double for loop to find our sum if this was unsorted. And in fact, I actually think it makes more sense to run that double for loop when it is unsorted, because when it's unsorted, there's like really no ordering. You quite literally have to go through every single element a few times just to see if we can find like the answer, at least as like a brute force. But like in this case, we have a sorted array, and I think that's a pretty crucial piece of information. Now, when something is sorted, my mind kind of goes towards like binary search, but in this particular situation, I don't think it makes sense to use a binary search, just because what if our indices were so far away from each other? Like if we had this index and this index, I really feel like a binary search couldn't get those two indices Or it could, but it would just be like super difficult to implement. So, is there some other way where we can use the fact that it's sorted to help us in this particular situation? Well, if you guys remember, in our last brute force implementation, the very first thing we did was initialize 2 pointers in the beginning. Now, if I am ever working with 2 pointers, and if I need to change it up somehow, and I just don't know where to start, the first thing that I do is just move one of the pointers somewhere else. And in this case, I'm just going to move one of the pointers at the end. Okay? Now that I've done this, I've actually opened up myself to full control to the fact that this is sorted. Why is that? Well, we know that all the smaller numbers, or the smaller value numbers, are like on this left-hand side, and all the larger value numbers are on the right-hand side. And that actually gives us a lot of value, because if our temporary sum was ever greater than our target sum, all we'd have to do is move our larger value down one to make it a little smaller. And also, if we're looking at it from the opposite point of view, if our temporary sum was actually smaller than our target sum, all we have to do is move our left pointer up one or to the right one to make our overall temporary sum larger. And that is actually super beneficial to us and very helpful. And that's actually how we're going to solve this problem. So once again, let's just kind of go through that example with the example that was provided to us on Leetcode. Now here, what is our temporary sum? Temporary sum is 17. Is 17 greater than or less than our target sum? It's greater than. So what would make more sense to move? The I index, which is always going to be on the left, or the J index, which is going to be on the right? Well, if we move the I index up one, right, that would mean that our temporary sum would become 22. It became larger, right? But we want our temporary sum to become smaller. So what would make more sense is if we moved the right pointer, the J pointer, to the left. And when I do that, the temporary sum becomes 13. It becomes smaller. It's going in the direction that we want it to go in. And now, once again, is 13 greater than or less than our target sum? It's still greater than. So what are we going to do? We're going to move our J index, our right index, left one more time. And in doing so, our sum becomes 9. It becomes smaller. It goes in the direction that we want it to go in. And now we have a sum of 9. This is the sum that we're looking for. And hence, we can stop here and we can return that value. And look, did we have to go n squared to find that solution? Did we have to iterate through all the indices to find that solution? No. And maybe, this particular situation wasn't the best to use, because even in the brute force solution, all it took was our pointers to be in the beginning to find it. But what if we had this example? Now, with this example, we're going to look for the sum 22. And that sum can be attained when we have 9 and 13 here. Okay, so let's just go through our implementation the way we did, where we have a pointer in the very beginning and a pointer at the very end. And let's initialize our temp sum. Okay, so what's our first sum that we start off with? We have 18. Now, is 18 less than or greater than our actual sum? It's less than. So what are we going to do? We're going to move our left pointer up one. And when we do that, we're going to calculate the sum again. This time, the temporary sum is 24. So is 24 greater than or less than our actual sum? It's greater than. So what are we going to do now? We're going to move our right pointer to the left one. Okay, and in doing so, we're making our sum just a little bit smaller. Now, what's our new recalculated sum? It is 17. Okay, now, is 17 greater than or less than our sum? It's less than. So once again, we're going to move our left pointer up one, and by doing so, we're making our temporary sum of a greater value than it currently is. And what's the sum that we get from that? It's 22, and that is the answer that we're looking for. So now, by doing so, you see, we're only going through each element at a max of one time, and that time complexity is O of n. Now, if we had to do this in our brute force manner, look at what would have happened here. We would have first initialized 2 pointers in the beginning, and then we'd move one all the way down, and then we reset this one, and we move the I index up one, and then once again we move all the way down, and then we reset this one here, and we move the I up one, and then we'd finally get it. We have to go through this element once, and then these two elements again, and then these three elements another time, or rather these two elements another time, just to get our answer. That's why that is a brute force solution. We keep revisiting values that I guess we already have information to. In this new two-pointer solution where we're just incrementing and decrementing whenever we need to, it's actually an O of n time complexity, and it's much more efficient. So let's go ahead and code that out. Let's code out the better solution. So I'm going to comment this out, and in our new solution, we're going to need 2 pointers. One at the very beginning of our index, of our array, which is going to be at the 0th index, and one at the very end. So I'm going to put this at numbers at length -1. So it says that we can't use the same element twice, and that would be when I equals j. So what I'm going to do is I'm going to say while I is less than j, strictly less than j, we're going to calculate a temporary sum. And so I'll do that. Int temp sum equals numbers I plus numbers j. And that's what we were doing in our example. We would initialize our pointers, find a temporary sum, and compare that sum to the actual sum. So let me say if temp sum, this is called target, so if temp sum equals the target, that means we found our answer. We don't need to proceed any further, so let's just go ahead and return those two indices. So return new int I plus 1, j plus 1, because remember, they're not 0 index. Now, there are 2 other cases to consider. If our temporary sum is less than our target sum, and if our temporary sum is greater than our target sum. So let's just put those conditions out. Else if temp sum is less than our target, if it's less than our target, we're going to want to increment our I pointer up 1 so we can make our total temporary sum a little bit bigger than it is right now. So all I'm going to do is increment I. And if the temporary sum is greater than our target, I don't need to do else if, but in this case I'll just do it so we can see it very clearly. If our temporary sum is greater than our target, that means we need to decrement our j, our right pointer, down 1 so we can make our temporary sum a little smaller than it is. So I'm just going to decrement j. And this will give us the code that we need to find our answer. Now, obviously we need another return statement, so I'm just going to say if for whatever reason it has like a weird test case, then it'll return null. But this should never actually go off, so I'm going to go ahead and run that. That works, and let's submit it. Perfect. Our runtime goes from 248 milliseconds all the way to 0 milliseconds. Would you look at that? That time complexity is O of n, just because we go through each element only 1 time in the worst case. And once again, space complexity is also O of 1. So yeah, guys, that's how you do that problem. If you found any value from this video, please give this video a like and subscribe to this channel. Also, if there's any other problem you guys want me to do, just let me know in the comments and I'll make sure to do them for you, and I'll even tag you when I do them. I hope you guys have a good rest of the day, and I'll see you guys next time.
I became famous for flaming you fuck, naming my way through the brush. There was no training or taming of me and my bruh. Live like a man, but I'm animal raw. We are the murderers there. Dealt with the jail and we murdered the murderers there. Then went to hell and discovered the devil delivered some hurt and despair. Used to have power to push, now I smoke pounds of the push. Holy, I'm burning the bush. Now